In this video, we're going to carry out a statistical test to analyse the country of Ikalpon. Now, we're told that in 2008, the average wages for graduates was £20,000 in Ikalpon. And we have randomly sampled 50 graduate wages and constructed a sample mean of their wages, which remember is equal to 1 over n times by the sum of the observations, such that for 50 observations of yi, we get a sample mean equal to £21,350. Now, before we can test anything, we need to think about what we know about this population. We do not know the variance of wages, so we do not know the variance of y within this economy. So we're going to need to estimate this using a ideally unbiased estimator. Now, before we try and construct an estimate, I'm going to make some assumptions about the data. These may or may not be good assumptions. The key assumption I'm making is that because we've been told that the observations are randomly sampled, we might assume that the observations are IID. So in other words, the expectation of each of the yi's is equal to the expectation of y, and also the variance of yi is equal to the variance of y, and that would be true for all observations of I. The other thing that follows from the observations being IID is that the covariance between observations are equal to 0. Now, we want to construct an unbiased estimator estimate of the variance of y. And we know an unbiased estimator, which is s squared. And s squared is, remember, equal to 1 over n minus 1 times by the sum of the y minus y bar squared. Now, we're told what the sum of the y minus y bar squared is in this example, and we know that there are 50 observations, so we can construct an estimate of the variance of y as being equal to 1 over 50 minus 1, or 1 over 49, times by the sum of the y minus y bar squared, or 1,744,189,453. So let's write that down. 1,744,189,453. And if we calculate our estimate, this gives us an estimate of the variance of y equal to 35,595,703.122. Now, this is almost certainly not the true variance, but this is an unbiased estimate of the variance of y. Now, whenever you're carrying out a test, it's often useful to think about what the distribution of your estimator that you're interested in is. Now, our estimator for the population average is the sample mean. Remember, the sample mean is just equal to 1 over n times by the sum of the observations. Now, by the central limit theorem, we know that provided there are a large enough sample, so that's more than about 30 to 50 observations, the sample mean will be approximately normally distributed, centered on the expectation of that sample mean, with variance equal to the variance of the sample mean. Now, from our assumptions earlier, we assumed that the observations were randomly drawn from the population and were independent and identically distributed. If that's true, the expectation of the sample mean is just equal to the expectation of y, and the variance of the sample mean is just equal to the variance of y divided by the number of observations. Now, when we're carrying out a statistical test, we will often assume that some null hypothesis is true. And an obvious null hypothesis to test here would be that average wages haven't changed. So our null hypothesis might be that the expected value of y is equal to £20,000. Now, if that null hypothesis is true, we could substitute in the expected value of y is equal to £20,000. Now, we still don't know what the variance of y is. So we're going to need to leave that as a general variance of y term. Even though we've got an estimate, here, this is not the true variance. So if we're writing down the approximate distribution of y bar, we can't just assume that this is the true variance of y. So when we're writing down the approximate distribution of y bar, it'll be approximately normally distributed. If our null hypothesis is true, that will be centered on 20,000, and we'll have variance equal to the variance of y divided by our sample size. Our sample size here is 50, so it'll be the variance of y over 50. So we want to finish this off by formally testing the null hypothesis that average wages haven't changed since 2008. So in other words, the expected value of y is still equal to £20,000 against the alternative hypothesis that the expected value of y is not equal to £20,000. So in other words, that the average wages have changed. Now, we're using an estimate of the variance of wages. So we're going to construct a t-statistic, which is just equal to our estimated sample mean minus the expected value of that sample mean if the null hypothesis is true, divided through by the estimated standard error of the sample mean, or the square root of the estimated variance of y bar. And we put a hat on that variance because it's to indicate that it's a estimate. So what do we know? Well, we already know our estimate of the population average is £21,350, so that will put in place of y bar. We know if the observations are independent and identically distributed, then if the null hypothesis is true, the expected value of y bar will just be equal to £20,000. We also have an estimate of the variance of y. We've got s squared as our estimate of the variance of y, and to get an estimate of the variance of the sample mean, we simply take an estimate of the variance of y and we divide it by the number of observations. Because remember, this is based on the fact that the variance of the sample mean is just equal to the variance of y divided by the number of observations. Our s squared is equal to 35,595,703.122. Our n is 50, so our estimated variance of the sample mean is going to be equal to 711,914.062. So now let's substitute our numbers in. Remember, our sample mean is 21,350. We're going to substitute in our estimated variance of y bar of 711,914.062, and we're going to substitute in our hypothesized value in place of the expected value of y bar if the null hypothesis is true, which will give us a t-statistic that looks something like this. So the t-statistic is equal to our estimate, 21,350 minus the hypothesized value, or minus 20,000, divided through by the estimated standard error of the variant, divided through by the estimated standard error of the sample mean, but we have our estimate of the variance of the sample mean, which is 711,914.062. So we're going to divide through by the square root of that estimated variance, which gives us a t-statistic equal to 1.60. Now, in this case, we've got 50 observations. Remember, when we estimate the variance of y, we lose a degree of freedom. So we're going to have to look up the critical value from the t-distribution with 49 degrees of freedom. And if you look up the critical value at the 5% significance level, you'll find that the most extreme 5% of outcomes are to the right of 2.01 and to the left of minus 2.01. So if we had a test statistic lying within the shaded area, we would reject our null hypothesis. But in this case, our test statistic was 1.60. It lies roughly there. Because it's not in the rejection region, we would fail to reject the null hypothesis. That means that we do not have enough evidence to reject the hypothesis that average wages are £20,000 per year.